Okay, so here are the notes for section 6.3, supplemental notes for section 6. Proving quadrilaterals or parallelograms. So the book has 4 theorems in this section. The first one is basically the first 3 are actually theorems we've already had, but backwards. So 6.9, we already know that earlier in the chapter that if you have a parallelogram, opposite sides are congruent. Well, section theorem 6.9 says if both pairs of opposite sides are congruent, then it is a parallelogram. Same thing with 6.610. We knew in section 6.2 that if you had a parallelogram, opposite sides are congruent, or opposite angles are congruent. Well, now theorem 6.10 says, okay, if you have a quadrilateral and your opposite angles are congruent, we know it's a parallelogram. Theorem 6.11, again, we also had this in section 6.2. If you had a parallelogram, the diagonals would bisect each other. So theorem 6.11 says, okay, great, you've got your diagonals bisecting each other. That means it must be a parallelogram. Now 6.12 is the new one. That's one we didn't do in section 6.2, and that's because this didn't need to come up, because if you have opposite sides congruent, you automatically have one pair of opposite sides congruent. And by definition, a parallelogram is a quadrilateral with both pairs of opposite sides parallel. So 6.12 is the only one that's really specific to section 6.3. So basically just says this: if one pair of opposite sides, so AB and DC, are both congruent and parallel, it has to be a parallelogram. So here's kind of a visual little thing I threw together for class to show you this, how it kind of works. So here's the same one I used in class. So what I've got it set up as is no matter what, segment AB and segment CD are congruent. They're actually this length here, of whatever this little guy here, A says. So if I make one bigger, it makes the other one bigger. They're the exact same size. And I've also made it so that they're both parallel to each other. So AB and CD, no matter what, they're parallel. So if I move this, they move in the same direction. And as you can see, as I move things around then, it forces BC and AD to be congruent and parallel as well. So no matter what, these two sides are going to be congruent. They're also going to be parallel. There you go, it's a parallelogram for their two sides. So hopefully it's pretty easy to see as I'm just going to kind of move this point around. Okay, I'm moving this side, keeping those parallel. It keeps those two guys parallel here that are dashed, and it keeps them congruent as well. And if I make this bigger or smaller, all it does is just distort where they're at. So basically, it's kind of a quick summary then. The book has these 5 ways basically to show you have a parallelogram. Okay. This is at the end of the section. So the first way is to show that both pairs of opposite sides are parallel. That's by the definition, which is true. That's the definition of parallelogram. Quadrilateral, both pairs of sides parallel. There's a bunch of different ways to do this. You can show corresponding angles are congruent, consecutive interior angles are supplementary, so on and so forth. One of the things the book does do is they'll use the slope formula to show that the slopes are equal. If you can show your slopes are equal, you also have a parallelogram. That's using the coordinate proof process, and we'll look at actually an example like that as a warm-up, or as a practice problem. If you can show that both pairs of opposite sides are congruent, whether that's through a good old 2-column proof or a solve for x, or using the distance formula. Okay, they will also use the distance formula from time to time to do that. Another way is to show that opposite angles are congruent. There's no distance midpoint kind of formula for that. The only way you're going to ever be able to do that is if you can show that they're congruent through some sort of like 2-column proof method. To show that the diagonals bisect each other, there actually is a trick to do that as well, besides just showing that the side parts are congruent. What you can do is if you have a parallelogram, I'm trying to sketch one as best I can down here. Okay, and if you draw on the diagonal and they truly bisect each other, this point right here is the midpoint of this diagonal and this diagonal. So we can use the midpoint formula to show this. And we'll do that from time to time. Not today, but in this example I'm going to show you because I don't have that much time to go through every single problem. But you'll see through some of these in class we do it from time to time. And then show that both pairs of sides are parallel and congruent. If we want to do that, we would use the slope formula for parallel, and then we'd use congruent, we use the distance formula. So again, we have 5 ways to do this. Show both pairs of opposite sides parallel. Again, you can do it through a 2-column proof. If you don't use a 2-column proof, you're going to use it by doing slopes are equal. Show that both pairs of sides are congruent. Again, either doing that in a 2-column proof or by the distance formula. The only way we can really do the angles congruent is if you're going to use the two-column proof method. To show the diagonals bisect each other, again, you could do a two-column proof, or more likely midpoint formula. And then to show that a pair of opposite sides is both parallel and congruent, slopes which other are parallel, distance formula which other they are congruent. Okay, so here's the first kind of example out of the book that some people struggle with. In this example, this is 1A and 1B. It's from the notes and the practice part from the book. They want us to show that these are parallelograms. So for 1A, we have to go through and do one of our 5 methods. And hopefully you can look at this one and say, oh, well, the other both 5 and 5 and 12 and 12. So yes, both pairs of opposite sides are congruent. Okay, sloppy, but that gets, yeah, that's enough. Now 1B is tricky because in 1B we have a pair of sides that are congruent. Okay, we have a pair of opposite angles that are congruent. Now, what that forces us to try to figure out is there a way that one pair of opposite angles could be congruent, and to show then that these guys here would not be, that these angles here are congruent, or that these two lines here are parallel. Okay. So that's going to be our issue we have to sort through for this problem. Okay. So looking at this one, right now it's hard to get past the fact that it does look so much like a parallelogram. But the problem is I don't know for sure what these two angles are. And so since I don't know that, I can't assume that these guys are congruent. And unfortunately, the only way I could find out what their angles would exactly be is if I did assume those were parallel, and they're not told to be parallel. So this one is one of those very difficult, tricky problems where the book's like giving you a drawing that is clearly a parallelogram. There's no way this drawing is not. They've given you two situations that look to be true. Well, actually, although these actually look obtuse, and that's 85, so they would be more than 85, but regardless, where those definitely do look congruent, and these two guys here definitely are congruent. But because we don't have a pair of sides that are congruent and parallel, or two pairs of opposite angles that are parallel, or that are congruent, we can't say for sure that it is. So even though it's drawn like it, it doesn't fit one of our 5 cases. It misses any of them. Now, the last problem I want to look at is number 24 from the homework. This is one that a lot of times people get stuck with. First of all, plot it out. So I gave myself some graph paper here. So A is at -3, 4. B is at 4, 5. C is at 5, -1. And D is at -2, -2. Doesn't have to be a beautiful sketch, although graph paper does help tremendously. Looking at that does look like a parallelogram. Looks like the opposite sides are parallel. But we have to use the slope formula to do that, which is y2 minus y1 over x2 minus x1. Okay. So, I have to find the slopes of sides BC, AB, DC, and AD. So, let's just do AD first. It would be -2 minus 4, which is -6, over -2 minus -3, which is +1. Slope is -6. Okay. Now the side that AD corresponds with is BC. So, the slope of BC. So BC is 5 minus 4, which is 1. Sorry, strike that. Wrong. -1 minus 5, which is -6. And 5 minus 4, which is 1. Again, gives us -6 for our slope. So these two guys here are both parallel to each other because they have the same slopes. Now, AB and DC, we're going to show that they're parallel by having the same slope as well. So we do the slope of AB. So y minus y for AB is 5 minus 4, which is 1. And then the y minus y, or x minus x is 4 minus -3, which is 7. So AB has a slope of 1/7. Okay. Now our next hope is that DC has the same slope as well, because if it does, then we obviously have excuse me, another set of parallel lines. So D is -2 minus -1, which is -1, over -2 minus 5, which is -7, 1/7. So these two lines are also parallel. Okay. So again, what we're trying to do for this one is to use the slope formula to prove that this is a parallelogram. The only way the slope formula is useful to us is to show that if two things have the same slope, they're parallel. So what we did for this one was we did the slope formula for all four sides, showed that AD was the same as the slope as BC, showed that AB had the same slope as CD, therefore both pairs of opposite sides are parallel. And that's this example here.